Hello, in the previous video we talking about refrigerator and heat pump and using clause statement to understand how this work. The process from the heat transfer can only go from hot to cold, but how do we achieve the purpose to go from lower temperature to hot temperature in both refrigerator and heat pump, and knowing understand how that cycle works? That was our goal before. And now this video we're going to look at reversed Carnot devices. So in the previous series when we're talking about heat engine, we talk about actual heat engine, and we're also talking about reversed Carnot heat engine and heat engine. This is the same concept, so very similar. So if it's Carnot, we understand it's going to be ideal situation. It's not actual. And because it is not actual, it reaches this maximum efficiency. So here basically COP, coefficient of performance, reaches its own, it has like maximum efficiency. You get higher value on that. So now let's take a look. If it is COP for refrigerator, and now it's let's don't get there yet, and that is equal to, for refrigerator we required work come in, and we desire there's more heat transfer from lower temperature reservoir, which is refrigerator space, to the higher temperature reservoir, which is our kitchen, so QL over WA. And we also say WA, the work required A, is basically your QH minus your QL. Okay, then let's write it down. Our COP for our heat pump, the desired here is different. We want actually more heat going to the hotter environment, which is your cozy warm room, and the required work. So in that situation, we will have QH, and work A is going to be QH minus QL. Okay. So how about for Carnot cycle? That's where the new element will be. For COP, for refrigerator, for Carnot, or the maximum, whatever we call this, it's going to be replace the Q, the huge heat transfer, with the temperature. So QL corresponding to the lower temperature, QH is going to be corresponding to the higher temperature reservoir. So this is going to be our new formula for Carnot efficiency. Now for COP coefficient of performance for heat pump and for Carnot, which is maximum efficiency, then that would be equal to QH. Here is the heat transfer corresponding to the higher temperature reservoir TH, and this will be TH minus TL. So that's our new equations to describe the Carnot cycle, Carnot efficiency for both refrigerator and heat pump. Okay, now let's look at a quick example. So here's the inventor claim that this refrigerator is gonna be maintained at 2 degrees and the room temperature is 25 and have a COP of 13.5. Is that possible? Is that truly true? So then we can quickly go ahead and draw our refrigerator cycle. And we know this is going to be TH. This will be our TL. And for TH, we're going to transfer heat from cold to hot. And in order to do that, we have to have a work coming into the system. And here is our cycle, and we call this refrigerator cycle. Now, let's go ahead and label those temperature. So here the temperature, the hottest temperature, which is our kitchen environment, and here is a room that's 25 degrees Celsius. And TL, this refrigerator space, is 2 degrees Celsius. And now let's go ahead and calculate what would be the highest possible COP for this refrigerator. So maximum, or we can call Carnot. That's going to be this equation, right, for refrigerator. So it will be TL over TH minus TL. And our TL, the lowest temperature we could get is 2, but we cannot choose 2. We have to add what? 273, because we gotta have to be used in Kelvin. Just like in the Carnot heat engine, you have to use the absolute temperature. So plus 273, and TH minus TL, 8 TH is 25, then minus 20 minus 2 degree. And here, since it's a temperature difference, we know delta T in degrees Celsius is same as delta T in Kelvin, so we don't need to worry about conversion there. And with that, you can calculate our COP for this heat pump. The answer I got here is 11.96. No unit, right? Because they cancel out the Kelvin and Kelvin. Just like efficiency, there's no unit. So COP for this problem is 11.96. And be aware, this is absolutely what? The maximum we could ever do. The best we could ever do with this condition given. Those conditions are 25 degree and 2 degree. Because we know this from previous discussion. If this temperature gets higher, or this lower temperature gets lower, we'll get higher performance, higher efficiency, right? But with what we have, the maximum we can get is 11.96. And however, this inventor claim can have 13.5, which is greater than this maximum value. We could have 11.96. That tells us this is bluffing. This is not possible. It's impossible. Okay? All right, so that's come up. That will be the end of this discussion about Carnot refrigerator and Carnot heat pump. All right, I'll see you next time. Bye.